going to talk about sets, set terminology, because sets and probability are very closely related, because if you think about all a sample space is a set of outcomes. Now a set is just a collection of objects, and we call them elements. So some language behind it. We can have listing sets, where you simply list everything that's in the set. But you could also have a describing set where rather than writing what the elements are, you describe them. And so the set A there, instead of writing 1, 3, 5, I could say, oh look, first 3 odd numbers. Equal sets are 2 different sets that have exactly the same elements. Set B here, 5, 3, 1, would be equal to set A, which is 1, 3, 5. They've got the same elements. The empty set is the set that contains no elements. So it's sometimes called the null set. Whereas the universal set is one that contains every possible element. That'd be like our sample space, I guess, in probability. Subset is a set that's contained within another set. So here's another set here, C, which is simply the number 5. That would be a subset of both A and B as well. Intersection, that's how the sets overlap, so the things they have in common. Intersection A and D would just be 3. 3 is in both of those sets. Union is when you combine the sets together. So the collection of all of the objects. 1, 2, 3, 4, 5 now would be the union of those 2 sets. Complement, again, just like in probability we have complementary events, are all the elements that are not in the set but are in the universal set. So the complement of A would be 2, 4, 6. Notation then. How we represent the empty set, it could simply be braces with nothing in it, or this symbol, the 0 with the slash through it. That also represents the empty set. Well, looks like an E, is an element of. So 3 is an element of the set A. The absolute value signs, another way of saying magnitude, so basically it's the size of the set. Or we might write N and then list the set inside the parentheses, with the number of things in there. A sideways U, I guess you could think of that, is subset. C is a subset of A. C is also a subset of B. This one's interesting. B is a subset of A, but it's also an equal set. So we also put a line underneath to indicate it's also the equal set as well as a subset. And the very last one, the empty set is a subset of every set, which is weird because it contains something, but we're saying nothing is a subset of something. But it is a subset of every set. Intersection, the upside down U, and union, the right way up U. Complement, remember in probability we wrote the events with the bar over the top. Same idea, we write A with a bar over top. Although in sets there are other ways of writing the complement. A with a dash, or even A with a C I've seen. But probably the bar is the most common way of doing it. The complement of A. That brings us to Venn diagrams, another way of listing our objects. The universal set we represent as a rectangle. That's always a rectangle, and then all the other sets are inside that rectangle. There is a picture of all of those sets I just talked about inside a Venn diagram. C was a subset of B. If you look at the Venn diagram, you'll see that C is totally within B, so it is a subset of B. The intersection, well, that was the overlapping part. 3 was the intersection of A and D. Union were the sets joined together. So 1, 2, 3, 4 was the union of A and D. The complement of A, well, A was 3, 1. The complement is everything that's in the universal set, but not in the set A. That's how a Venn diagram would look for that one. And then finally, what we call disjoint sets. Sets that have no point of intersection. In probability, we call those mutually exclusive events. And you can see there's no intersection between C and D. So how can we use Venn diagrams as a way of counting for probability problems? because just like we saw in perms and coms, we're more interested in the number of elements rather than what each of the individual elements are for probability. The counting rule. The number of elements in A union B would be the number of elements in A plus the number of elements in B minus the number of elements in the intersection. And that's what we saw in probability about the double counting. Remember how we had to subtract things that were double counted? And that's essentially what this is doing here. It's subtracting the things that have been double counted. Let's have a look at this HSC question then. History and geography, 2 subjects, group of 40 students, and this is what we know. 7 students study neither history or geography, 20 study history, 18 study geography. A student is chosen at random and they actually asked you to draw up a Venn diagram for this, although it did say or otherwise, so you could do it another way if you wanted to. Find the probability that the student studies both history and geography. A universal set. Inside that universal set, we've got students that study geography, students study history, and there is an overlap. Let's fill in the numbers. They told me 7 do neither, so I know there's 7 not inside those 2 sets. Okay, now I've got to calculate all the missing information. There's my formula. We know G union H must be 33 because there are 7 objects in the universal set that are not in that. So by subtraction, there must be 33 that are contained within those 2 sets. The number of students studying geography was 18. The number of students studying history was 20. So now I can work out how many are in that intersection. Simple subtraction, we get that there are 5 in there. And now I can complete that Venn diagram, which means there must be 15 other students in history, because there was 20 all up, and 13 in the other section of geography. To find now the probability they study both, I look at the intersection, 5 over 40, 1 in 8. Students chosen at random. Given that he studies geography, what's the probability that they do not study history? So now we're told they do study geography. So if you like, geography has become the universal set for this problem. And we want to know that they don't study history. So just looking at the geography set, I can see, well, there's 13 that study geography but do not study history. Therefore, 13 out of 18 students that study geography, there's my probability. As I say, it's another way of listing the information without having to list every piece of information. It's just more the number of things that are in those sets. 2 students are chosen at random, one after another. What's the probability that the first student studies history and the second student does not study history? So probability of H, then not H. 20 out of 40. But then the next one will be 20 out of 39 because we've already chosen one of the students, so now it'll only be over 39, and that gives us 10 out of 39. So 12C and 12D using Venn diagrams to help us solve probability problems.